Hello students, welcome back to session 5 of linear transformations. So in the last class you studied what is meant by matrix of linear transformations. Means if T is an operator on a vector space V or T belongs to A of V, then this T under the basis of V, say V1, V2, etc., Vn of V, okay, has a matrix, say, that is denoted by m of t. And also we have studied that if we change the basis of a vector space V, that means we know that a vector space can have more than one set of basis elements. Say the basis we change it as V1 dash, V2 dash, etc., Vn dash. Then we get, say, this is matrix m1 of t, I may call. So under this, with respect to this basis, matrix of T will be, say, m2 of T. Both corresponds to the same linear transformation T. Okay. Now the question is there any relation between these m1 and m2? That is also we have given the relation between these two is m2 of T is equal to C into m1 of T into C inverse, where C is the matrix of change of basis. That theorem we also proved, and we have proved a few, and we have solved few problems related to the matrix of linear transformation and the matrix of change of basis. Means given a linear transformation T, so if they given the matrix of this transformation, then we calculate how the transformation looks, how the nature of the transformation, and also we calculate the matrix of change of basis, okay, with respect to one basis and with respect to the other basis also. Okay, so we have given the counter example for this theorem. Okay, now let us and also yes, let's continue. Before continuing on this topic, let us prove few results which we have left in the few before as last class. Okay, so first let us take up one result. Say, suppose we have a linear transformation T from V to V. Then this linear transformation is 1, 1 if and only if it is onto. So this result already we have used. Okay. So the transformation T is 1, 1 if and only if T is onto. Okay. For this, let T from V to V be a 1, to 1 linear transformation. Let dimension of V be n, and let V1, V2, etc., Vn be a basis of V. Now consider alpha 1 into T of V1 plus alpha 2 into T of V2, etc., alpha n into T of Vn is equal to 0 mean. Okay. So this implies, since T is linear, this can be written as T of alpha 1 V1 plus alpha 2 V2, etc., alpha n Vn, that's equal to 0. 0 means T of 0. Okay. So since T is assumed to be 1 to 1, this implies that T of x is equal to T of y means x is equal to y. Accordingly, alpha 1 V1, alpha 2 V2, etc., alpha n Vn is equal to 0. Now this is equal to 0 and V1, V2, etc., Vn is a basis, means they are linearly independent, so that each alpha will be 0. Now we have taken alpha 1 T of V1, alpha 2 plus alpha 2 T of V2, etc., alpha n T of Vn is equal to 0, and we have shown that each of the scalar coefficients alpha is are zeros. Therefore, by definition we can declare that the set T of V1, T of V2, etc., T of Vn is linearly independent. So if they are linearly independent, then as the dimension of the vector space is n, then any set of n linearly independent vectors forms a basis. Accordingly, this set forms a basis of the vector space V. If this is a basis of the vector space V, means any vector in V can be written as a linear combination of these basis elements. So if I take x to be any element of V, then this x can be written as, say, alpha 1 T of V1, alpha 2 T of V2, etc., alpha n T of Vn. So this is equal to what? T of alpha 1 V1, alpha 2 V2, etc., alpha n Vn. So this is equal to T of y, where y is what? The linear combination of these. Definitely that will be in V only. So T of y is equal to x. Means if we take x belongs to codomain V, then there exists an element y belong to domain space such that the image of that element under T is X. Therefore, by definition, T is onto. Okay, T is onto. We have assumed that T is 1, 1 and we have shown that T is onto. Okay, conversely, let us assume that T is onto. So, if I take T is onto, then we will show T is 1, 1. So, for this, let Y belongs to V. Now, Y belongs to V, the codomain space means there exists, since T is onto, there exists some element X belongs to domain space V such that T of X is equal to Y. Now, again X belongs to V implies what? X can be written as a linear combination of basis elements that I written in the summation notation as summation I is equal to 1 to n alpha I Vi, or this can be written as alpha 1 V1, alpha 2 V2, etc. plus alpha n Vn, where each alpha I belongs to F. Therefore, Y is equal to T of X. T of X is equal to what? T of summation I is equal to 1 to n alpha I Vi. So, this is equal to summation I is equal to 1 to n alpha I into T of Vi. Okay. So, the element Y belongs to V can be written as linear combination of T of Vi's. Means what? These T of Vi's means T of V1, T of V2, etc. T of Vn spans V. Again, as dimension of V is n, these elements forms a basis of V. T of V1, T of V2, etc. T of Vn forms a basis of V. Therefore, what will happen? Now, if X belongs to kernel of T, be any element, then what will happen? By definition of a kernel, T of X is 0. T of X means what? T of summation I is equal to 1 to n alpha I Vi, because X is a linear combination of basis elements. This will be equal to 0. This is equal to what? Summation I is equal to 1 to n alpha I T of Vi is 0. Now, so these are T of V1, T of V2, etc. T of Vn is basis means they are linearly independent. Therefore, accordingly, each alpha is must be 0. Each alpha is must be 0 means what? X is the linear combination of these alpha i's means X must be 0. So, X is an any element of kernel of T, and that X itself is the 0 vector means what? Kernel of T contains only 0 vector. If the kernel of T contains only 0 vector, then by definition T can be declared as 1 to 1. So, we have assumed that T is onto and we have shown T is 1 to 1. Okay. Already I given this definition. Once again I am taking up. Say if T belongs to A of V, then the scalar lambda belongs to F is called an eigenvalue of T if there exists a non-zero vector V belongs to V such that T of V is equal to lambda times into V. This non-zero vector V in V such that T of V is equal to lambda into V is called the eigenvector corresponding to the eigenvalue lambda. Okay. So, now let us take up this example. So, suppose we have a mapping T from R2 to R2 be a linear operator defined by T of xy is equal to x comma 0. Now, if I assume that C is any eigenvalue of T, then by definition there exists a non-zero vector xy belongs to R2, such that T of xy is what? Lambda times into xy means C into xy. T of x is equal to is by definition of eigenvalue T of x is equal to lambda times x. Accordingly, T of xy is equal to C into xy. T of xy is our definition. T of xy is x comma 0 is C into x comma y. This implies that x can be written as x is equal to C into x, equating on both sides. So, 0 is equal to C into y. This implies C minus 1 into x is equal to 0 and C into y is equal to 0. Now, look here. Now, C minus 1 into x is 0 implies what? Either x is 0 or C minus 1 is equal to 0. C minus 1 is equal to 0 means C is equal to 1. Means either x is equal to 0 or C is equal to 1. Now, if x is 0, what will happen? If x is 0, then y cannot be 0. Otherwise, xy becomes a 0 vector. Okay, xy becomes a 0 vector means it cannot be a eigenvector. Okay, see, xy is a non-zero vector, so it cannot be an eigenvector. So, y cannot be 0. If y cannot be 0, then what will happen? C into y is equal to 0 means, and y cannot be 0 means C must be equal to 0. Okay, C must be equal to 0. Now, if C is equal to 0, if I assume that C is 0, then 0 is an eigenvector of T. Because here t of 0 1 is equal to what? T of 0 1 is equal to, by definition, 0 comma 0, because t of xy is x comma 0 means x is here 0, 0 comma 0, 0 comma 0 can be written as 0 into 0 comma 1. Therefore, t of x is equal to lambda times into x. Okay. For the 0 vector, for the 0 eigenvalue, there exists a non-zero vector 0 comma 1, which is the eigenvector. Therefore, 0 1 is the eigenvector corresponding to the eigenvalue 0. Next possibility is c is equal to 1. So now if c is equal to 1, what will happen? As x cannot be 0, so therefore y must be equal to 0. Possibility. If c is equal to 1, then because c into y is equal to 0 implies c is 1 means what? Y must be equal to 0. So that t of xy is equal to t of 1 comma 0 is equal to 1 0. Okay, because t of xy is x comma 0, x is 1, 1 comma 0, that's equal to 1. This can be written as 1 times into 1 comma 0. Therefore, 1 0 is an eigenvector of t corresponding to the eigenvalue 1. So, in this problem, we have calculated how the eigenvalue and eigenvector looks for a linear transformation t from R2 to R2. Now, note that if 0 is an eigenvalue of t, then what will happen? Then the non-zero vector v belongs to v such that t of v is equal to 0 into v, because by definition of a eigenvalue, t of is equal to 0 into v, but 0 into v is 0. So this implies what? V belongs to t of v is 0 means v belongs to kernel of t. Kernel of t, v belongs to kernel of t means what? Kernel of t is not equal to 0, because non-zero vector v belongs to kernel of t means kernel of t cannot be a only contains 0 vector. Therefore, it cannot, kernel of t is not equal to 0 means what? T cannot be 1 to 1. If t cannot be 1 to 1 means what? T is singular. If t is not 1 to 1 means t is singular, or in other words, the transformation which carries non-zero vector to 0 vector. Non-zero vector to 0 vector is always, you know that we have proved one theorem. A transformation which carries non-zero vector to 0 vector is a singular linear transformation. Therefore, t is a singular transformation, means if 0 is an eigenvalue, then the transformation is singular. Okay. Next, so eigenspace. Look at the eigenspace. So if c is an eigenvalue of t, then we define the set denoted by WC contains set of all v belongs to v such that t of v is equal to c times into v. Okay, we define WC is equal to set of all v belongs to v such that t of v is equal to c into v. Now clearly 0 belongs to WC, because t of 0 is what? 0, t of 0 is 0, 0 can be written as c into 0, therefore 0 will be belongs to WC, and so WC cannot be empty. Okay, so therefore I then S, WC cannot be empty. Let alpha comma beta belongs to F and V1 comma V2 be any two elements of WC. Then what will happen? T of alpha V1 plus beta V2. This is equal to, since T is linear transformation, alpha into T of V1 plus beta into T of V2. So alpha into T of V1 is what? C into V1, right? Plus beta into T of V2 is C into V2. Therefore, this can be written as C times alpha V1 plus beta V2. C times alpha V1 plus beta 2 implies what will happen? Say T of alpha V1 plus beta V2 is equal to C times alpha V1 plus beta V2. Then according to our definition of WC, alpha V1 plus beta V2 belongs to WC. Therefore, WC is a subspace of V. So, WC is a subspace of V. This WC is called the eigenspace of T corresponding to the eigenvalue C of T. Okay. So, WC is called the eigenspace, eigenvalue, eigenvector and the eigenspace. So, now let us take up the example here. So, suppose T is a mapping from R2 to R2 defined by T of xy is equal to x comma 0. This example we have taken up just now. Okay. Then we know that 1 is an eigenvalue of T. Okay. Now, W1 is equal to set of all xy belongs to R2 such that T of xy is equal to what? C into xy means 1 into xy. Means set of all xy belongs to R2 such that x0 is equal to xy means T of xy is what? By definition, x0 is equal to x into y. X is equal to x into y means what will happen? Say set of all x0 is equal to x into y means what? Y must be equal to 0. Therefore, this can be written as set of all x0 belongs to R2 such that x belongs to R2. Now, set of all points x0, y coordinate is 0, x comma 0 in R2 where x belongs to R means what? This is nothing but the x-axis. Okay, the eigenspace is the x-axis in R2. Okay, understand now? So, now the eigenspace WC is equal to set of all V belongs to V such that T of V is equal to C into V. So, set of all V belongs to V such that this can be written as T minus C into I of V is equal to 0. So, set of all V belongs to V such that T minus C into I of V is 0 means what? So, this is nothing but the null space of or kernel of the transformation T minus C into I. So, the eigenspace is nothing but the null space or the kernel of the transformation T minus C into I. Okay. So, WC is the null space of T minus C into I. These are the few results that been missed in the last classes. Okay. So, now I will continue the matrix of linear transformations again. Now, let us come to the important section, say, which is the canonical forms. Now, what are canonical forms? Let us discuss now. Okay. We know that if V is an n-dimensional vector space over a field F, then the linear transformations T1 comma T2 belongs to A of V are said to be similar. The transformation T1 and T2 are said to be similar if there exists an invertible linear transformation S in A of V such that T2 can be written as S into T1 into S inverse. So, T2 can be written as S into T1 into S inverse. Okay, so now the transformation T1 and T2 are said to be similar transformations if this condition holds true. Okay, or T1 can be written as S T S inverse, S or say U T T1 can be written as U T2 U inverse. Okay, so now this definition may be translated into matrices also, because we say the two matrices AB belongs to Fn are said to be similar if there exists an invertible matrix C belongs to Fn such that B can be written as CA C inverse. So, matrix 2, matrix C and B are said to be similar if there exists an invertible matrix C in Fn such that B can be written as CA C inverse. Now, this relation of similarity, if I define this relation on the set on the algebra A of V, if we define this relation on the algebra A of B, then this relation becomes an equivalence relation. Okay, definitely it becomes an equivalence relation because T1 can be written as T1 is equal to I T1 I inverse, means T1 is similar to T2. Similarly, we can show that T1 is, if T1 is similar to T2, then T2 is also similar to T1, and also if T1 is similar to T2 and T2 is similar to T3, then we can show that T1 is similar to T3. So, now therefore, this relation of similarity is an equivalence relation. So, and you know that every equivalence relation partitions or breaks up the set into disjoint subclasses called the equivalence class. So, here the equivalence classes are called the similarity class. Okay, the equivalence classes are called the similarity class. Now, the question is, suppose you are given two transformations, say T1 and T2. If they given T1 and T2, how do you declare that this T1 and T2 are similar? Suppose we have given two transformations T1 and T2. How do you say T1 and T2 are similar? For this, what we have to find? So, we have to find an invertible transformation, say S such that T2 is equal to S into T1 into S inverse. Finding, you know that while solving problems, finding this transformation S is not so easy. Okay, finding this S is also not so easy. And above all. Now, so suppose we have to find, say the other method is, say suppose we have T1 and T2. So how do you say, how do you verify that they are similar? Say first let us find out the similarity class of T1. This is, suppose this is the similarity class or equivalence class of T1. So if this equivalence class of T1 or similarity class of T1, if it contains T2, if T2 is belongs to in similarity class of T1, then we say T1 and T2 are similar. T1 and T2 are similar. This is a not a so easy procedure. It's a very feasible. It's not a so feasible procedure. Okay. So means what you have to do. So we have to take, say suppose we have so many say similarity classes, say T1, T2 and so on. There are n number of similarity classes. Suppose I will take one transformation, say U. Say I will ask whether U is similar to T1, U is similar to T2 or U is similar to Tn. Then what you have to do? You have to take up this transformation and you try to match up at T1. We will search for U as in this similarity class whether U is similar to this T1. Then if it is similar, then we say T1 and U are similar. Next we go on finding, verifying at T2 whether U belongs to the similarity class T2. If it is not, then we will go for the other. So likewise you need to verify, you have to take up this transformation at each similarity classes and you need to check whether U is present in this one, this similarity class, or U is present in this second similarity class, or U is present in nth similarity class Tn and so on. So again it is like it's very difficult task. Okay, so taking up a transformation and say it is like matching up. So you take some element, so matching up some heaps of, say some heaps of people or heaps of transformations are there. So we need to take U, whether U is present here in this heap of transformations. They again very difficult. Okay, now instead of that, say let us, if we have some particular, if you have some standard forms, say similarity class of T1. So the similarity class of T1 will look like some say this is like a upper triangular forms. Similarity class of T2 is say lower triangular forms. Similarity class of T3 is some other forms. Then we will pick up, you will check the matrix of this transformation U. So matrix of U you will find. If the matrix of U is upper triangular, then we say U and T1 are similar. If the matrix of U is lower triangular, then we say the matrix of this U is similar to the transformation T2, and likewise T3 may be some diagonal matrix or some other forms, particular forms. Okay, so there are certain particular forms of matrices. So we will find, suppose if you given the some transformation and if you need to verify whether that transformation is similar to any of these, say T1, T2 and so on, then we will go and verify whether we will find the matrix of T1. So there are nice forms already, we have standard matrix forms. So we will verify whether U is of that standard form, say upper, lower, diagonal and many others. Okay. So this is a very simple procedure. Okay. So then what will happen? So we will take up U and will verify at each similarity class. These standard matrix forms are called canonical forms. Canonical forms. Understand this? So there are standard matrix forms. These are called canonical forms. So some particular I define. So canonical form 1 will look like particularly like this. Means the matrix in this will look like particularly I define this. Okay. Then you will see the matrix of U. If the matrix of U is of that first form, then U is similar to that first form transformation. Next, likewise second, third and so on. There are plenty of canonical forms, but in your syllabus you will have three standard canonical forms. One is the triangular form, the other is the Jordan form, and the third one is rational canonical forms. So we will discuss these three canonical forms only. First one is triangular form, and the next one is Jordan form, and the third one is rational canonical forms. Okay. So now first let us take up the triangular form. Okay. Before going to discuss the theorem or the result based on triangular form, or what is the condition for a transformation, what is the condition for a transformation to be in the triangular form, let us take up one definition and a result based on that definition. Okay. So let us take up this. The subspace W of a vector space V, the subspace W of V is invariant under a transformation T if T of W is contained in W. So we say that subspace W is invariant under the transformation T if T of W is contained in W. Okay. Now this result says if the subspace W of a vector space V is invariant under the transformation T belongs to A of V, then T induces a linear transformation that is denoted by T bar on the quotient space V by W. You know how to construct V by W because W is a subspace, means we can construct the quotient space V by W. So T bar T induces a linear transformation or linear operator T bar on V by W defined by T bar of, how the elements of V by W looks, it contains set of all elements of the form X plus W or V plus W. So therefore T bar of V plus W is equal to, say, T of V plus W. Definitely T of V belongs to, so if V belongs to V, definitely T of V belongs to V. Therefore it is an element of V plus W. Therefore this is an element of again V by W. Therefore T bar is an operator on V by W because it carries elements of V by W to V by W. Okay. Now if T is an operator on V, then T introduces operator T bar on the quotient space V by W. The next thing is, if P1 of x is the minimal polynomial of T bar, if P1 of x is the minimal polynomial of T bar, means P1 of T bar is 0. Then, and if P of x is that for T, if P1 of x is the minimal polynomial of T bar and P of x is the minimal polynomial for T, then P1 of x divides P of x, or the minimal polynomial P1 of x is smaller than P of x. The minimal polynomial of T means P1 of x divides P of x. Okay. So let us prove this first. Now to prove this, say I will define the transformation as we said, say T bar from V by W to V by W by T bar of V plus W is equal to T of V plus W. Definitely T bar is defined in terms of T. Okay. T bar is defined in terms of T. Now first let us verify whether T bar is linear. So for this I will take up any two elements, say x comma y belongs to V by W. Now if x and y are elements of V by W, means how x looks, x can be written as V1 plus W, y can be written as V2 plus W, where V1 and V2 are elements of V. Let us consider alpha and beta be scalars. Then consider T bar of alpha x plus beta y. This is equal to T bar of alpha into x means V1 plus W plus beta into y means V2 plus W. So this is equal to T bar of alpha V1 plus beta V2 plus W. By definition, T bar of V plus W is T of V plus W because this is an element of V, because V is a vector space. Okay. So this is equal to T of alpha V1 plus beta V2 plus W. Since T is linear, I can write alpha into T of V1 plus beta into T of V2 plus W. So this can be written as alpha into T of V1 plus W plus beta into T of V2 plus W, because W can be written as W is equal to 2W because 2 belongs to F, 2 into W means W. Okay. So this is equal to alpha into T of V1 plus W plus beta into t of v2 plus w. This is equal to alpha into t of v1 plus w. I can write like this because alpha into w is w itself, plus beta into t of v2 plus w. So this is equal to alpha into t of v1 plus w means what? T bar of v1 plus w plus beta into t bar of v2 plus w. So this is equal to alpha into t bar of v1 plus w is what? X, plus beta into t bar of v2 plus w is y. So we have t bar of alpha x plus beta y is equal to alpha into t bar of x plus beta into t bar of y. Therefore we declare that t bar is linear. Okay, so t induces a linear transformation t bar, because t bar is defined in terms of t means what? T induces t bar, which is a linear transformation. One part is over. Okay, next let's come to the second part. Second part means what? So we have to show the minimal polynomial of t bar divides the minimal polynomial of t. So for this, look here. So first we show that here, if t satisfies a polynomial q of x belongs to f of x, then so does q bar. Means if t satisfies some polynomial, then t bar also satisfies that polynomial. First we will prove this. Okay, for this let x is equal to v plus w be any element of v by w. Now consider t square bar of x. So this is equal to t square bar of x means what? V plus w. Now t square bar of v plus w is what? According to our definition, t square of v plus w. T square of v plus w means what? T of v plus w. So this is equal to, now t of v is an element of v only again. Okay, therefore it is an element of v. T of v plus w means what? T bar of v plus w. T bar of v plus w can be again written as t bar of v plus w. So t bar into t bar means t bar square of v plus w. V plus w is x, so t bar square of x means t square bar of x is equal to t bar square of x. Therefore t bar is same as t square bar of x. T square bar is equal to t bar square. So similarly we can prove that tk bar is equal to t bar k for any positive integer k. Consequently, what will happen? If q of x is a polynomial with looking like a0 plus a1x etc. am x power of m, where a's are scalars in f of x, then q of t bar is same as q of t whole bar is same as q of t bar. Okay, q of t whole bar is same as q of t bar. If you want to prove this, say look here, q of t is what? a0 into I plus a1t etc. am t power of m. So now q of t bar means you take conjugate for this total. So as this implies a0 into I plus a1 into t bar and so on am into tm bar. Okay. So this is equal to a0 into I plus a1 into t bar plus a2 into t square bar means t bar square. Likewise am into t bar power of m. This is nothing but what? It's a polynomial in t bar. Therefore q of t bar. So q of t whole bar is q of t bar. Therefore look here, if t satisfies some polynomial say q of x, if t satisfies some polynomial say q of x, then by definition q of t is 0. If q of t is 0, then look here, q of t bar is equal to q of t whole bar. Q of t is 0, 0 bar means 0 itself, where 0 bar is the zero transformation on v by w. Understand now? So 0 bar denotes the zero transformation on v by w. It's not conjugate. So this is the transformation on v by w. Okay. Thus t bar satisfies q of x. If t satisfies q of x, then t bar also satisfies q of x. Now let us take up P1, let P1 of x be the minimal polynomial of t bar. Let P1 of x minimal polynomial of t bar. Now if t bar satisfies q of x, okay, if t bar satisfies q of x and P1 of x is the minimal polynomial of t bar, then by definition of a minimal polynomial, we already proved one result. minimal polynomial divides the polynomial satisfied by t. According to that, p1 of x divides q of x. So if p1 of x is the minimal polynomial of t bar and t bar satisfies q of x, means p1 of x divides q of x. This we already proved. Therefore, if p of x belongs to f of x, the minimal polynomial of t, then p of t is 0. If p of t is 0, then just now we have shown p of t bar is also 0, means t bar satisfies p of x. If t bar satisfies p of x and p1 of x is the minimal polynomial, means what? According to this definition, p1 of x divides p of x. So the minimal polynomial of t bar divides the minimal polynomial of t over f. Okay, this completes the lemma. Okay, now yes, note that if lambda belongs to f is the characteristic root of the transformation t belongs to a of v, then we know that, yes, in the last class we have proved this result, then lambda is a root of the minimal polynomial of t. If lambda is the characteristic root, then lambda is a root of the minimal polynomial of t. Therefore, all the characteristic roots of t, which lie in f, the field f, are the roots of the minimal polynomial of t over f. Okay, so if lambda is a characteristic root, then it is a root of the minimal polynomial. Therefore, all the characteristic roots of t which lie in f are the roots of the minimal polynomial of t over f. Therefore, we can say that the characteristic roots of t in f, therefore we say that all the characteristic roots of t are in the field f if all the roots of the minimal polynomial of t over f lie in f. Okay, understand now? So we say that all the characteristic roots of t are the eigenvalues of t are lies in the field f if all the roots of the minimal polynomial of t are in f. Okay, are in f. Now we say that, let us take up the first canonical form, which is the triangular form. So we say that the matrix is triangular. Triangular means upper triangular or lower triangular. Simply we say that the matrix is triangular if all its entries above the main diagonal are 0 or the matrix below the main diagonal are 0. So here we take up the matrix that will take up all the entries above the main diagonals are 0. So equivalently, T is a linear transformation over on V over F, then the matrix of T in this basis is triangular if, what will happen? T of V1 is equal to alpha 1 1 V1. So you already know that T of V1 is alpha 1 1 V1 plus alpha 1 2 V2 etc. alpha 1 n Vn. So all are zeros, alpha 1 1 Vn remains. T of V2 is alpha 2 1 V1, alpha 2 2 V2 plus alpha 2 3 V3 etc. alpha 2 n Vn. Those are all zeros. Only T of V2 is alpha 2 1 V1, alpha 2 2 V2. Similarly, T of Vn is alpha n1 V1, alpha n2 V2 etc. alpha nn Vn. Okay. So the matrix T, the transformation T is said to be of triangular form if this condition holds true. Or the matrix will look like this. See here, say this is A11, A11, sorry, A21, A22, all others are zeros, say, and continuing like this, AN1, AN2 etc. ANN. The all other terms are zeros except this. So this is the triangular form. Okay, understand now? So equivalently the matrix of T will look like, so T of V1 is equal to A11 V1, T of V2 is equal to A21 V1 plus A22 V2 only. So T of Vn is AN1 V1, AN2 V2 etc. ANN Vn. Okay. So now let's come to the first theorem of this triangular form. Say, so this is says if T belongs to A of V has all its eigenvalues or characteristic roots in the field F. If all the eigenvalues are lies in F, then we can find a basis of V in which the matrix of T is triangular. So triangular form exists only if all its eigenvalues lies in F. This can be taken as the criterion for the existence of triangular form. In the examination they may ask like state and prove the criterion for the existence of triangular form. We need to write this theorem. So look here, if T belongs to Fv as all its eigenvalues lies in F, definitely T, the transformation T, if it has an eigenvalue, definitely that lies in a field F. If it not lies in say the field R, we can extend it to the field C, definitely where all the eigenvalues are lies in that C. So every transformation has eigenvalues in F. Therefore every transformation can be bring it to triangular form. Understand this? Every transformation can be bring into triangular form. Every transformation means what? The matrix of that transformation can be bring it to triangular form. Okay, this is the theorem. So let us prove this theorem now. So we prove this theorem by induction, method of induction. Say method of induction means, say first let us take dimension of V over F is 1. Dimension of V is 1. Dimension of V is 1 means what? Then dimension of A of V is also 1. Dimension of A of V is 1 means what? A of V contains only a scalar. And so clearly the lemma holds true. We can vacuously assume that the lemma holds true. Suppose you assume that the theorem is true for all vector spaces over F of dimension up to n minus 1. Okay, we need to prove it for the dimension of V, that is n. So let V be of dimension n over F. Now they were given by hypothesis T as all its eigenvalues lies in F, because we have assumed that all the characteristic roots of T lies in the field F. Now let lambda 1 belongs to F be an eigenvalue of T. If lambda 1 is an eigenvalue of T, then by definition there exists a non-zero vector V1 belongs to V such that T of V1 is equal to what? Lambda 1 V1. T of V1 is equal to lambda 1 V1. Now let W be the subspace generated by this vector V1, means W is equal to multiples of V1, say A into V1, A where A belongs to F. Then what is the dimension of W? W becomes a one dimensional vector space because it is generated by single non-zero vector which is V1. Okay, and clearly W is also invariant under T, because if I take any element x belongs to W, then how x looks? X is equal to A into V1. So this implies T of x is equal to what? T of A into V1. Since T is linear, A into T of V1. T of A into T of V1, A into T of V1 is what? Lambda 1 V1. Now this can be written as A into lambda 1 into V1. Now A is an element of F, lambda 1 is an element of F, means A into lambda 1 is an element of F. Therefore element of F into V1 means what? It's a multiple of V1, therefore it belongs to W. Therefore if x belongs to W, T of x also belongs to W, means W is invariant under T. Okay, W is invariant under T. Now you put V bar is equal to V by W. Then what is the dimension of V bar? Dimension of V minus dimension of W. Dimension of V is n, dimension of W is 1. So therefore dimension of V bar is n minus 1. Now just now we have shown this T induces a linear transformation T bar on V bar whose minimal polynomial over F divides the minimal polynomial of T over F. Okay, just now we have proved accordingly. So if the minimal, look here, if the minimal polynomial of T, if the minimal polynomial of T1, T bar over F divides the minimal polynomial of T over F, means what? All the roots of, say look here, say if P1 of x divides P of x is the minimal polynomial of T, P1 of x is the minimal polynomial of T bar. So this means what? P of x can be written as, say, some u of x into, okay, some u of x into P1 of x. P of x can be written as, say, 2 divided 6 means what? 6 can be written as 2 into 3, means p of x can be written as u of x into p1 of x. Now if p1 of x is 0, definitely p of x is also 0, means the roots of p1 of x, the roots of p1 of x are also the roots of p of x. Are you understand now? So means the roots of the minimal polynomial of t bar are the roots of the minimal polynomial of t. So if the roots of p1 of x lies in f, definitely the roots of p of x also lies in f. Okay, means, so look here, we have assumed that the roots of t are lies in f, means the roots of p1 of x also lies in f. Right? Therefore, what will happen by the hypothesis of the theorem or by induction hypothesis? What will happen? If all the roots of p1 of x lies in f, then there is a basis of t bar in which the matrix of t is triangular. In which the matrix of t bar is triangular. Let us take up this now. Say we have, say, dimension of v bar is n minus 1. So there exists a basis v2 bar, v3 bar, etc. vn bar of v bar in which the matrix of t bar is triangular. Means this can be written as triangular matrix, means t bar of v2 bar can be written as a2 to v2 bar. Right? Up to n minus 1. I start with 2 and end at n. Okay? Means n minus 1. So t bar of v3 bar is equal to a3 to v2 bar plus a33 v3 bar. General element t bar of vi bar is equal to ai2 v2 bar, ai3 v3 bar, etc. aii vi bar, and t bar of vn is equal to an2 v2 bar, an3 v3 bar, etc. ann vn bar. Okay. So now v2 bar, if v2 bar can be written as v2 plus w, v3 bar can be written as v3 plus w, and so on, vn bar can be written as vn plus w, where v2, v3, etc. vn are elements of v, then certainly v1, v2, etc. vn forms a basis of v. Okay, because look here, dimension of v we assume to be n. So if you want to show these are basis, means it is enough to show that they are linearly independent, right? Because if the dimension of the vector space is n, then any set of n linearly independent vectors forms a basis. So we will show that v1, v2, etc. vn are linearly independent. Say you consider, for this you consider the linear combination, say c1 v1 plus c2 v2, etc. cn vn is equal to 0, where each ci belongs to f. Then what will happen? So this implies c2 v2 plus c3 v3, etc. cn plus cn vn is equal to, I will transform this to right, first term to right hand side, this becomes minus c1 v1. c1 v1 means this is a multiple of v1, definitely this belongs to w. Therefore c2 v2 plus c3 v3, etc. cn vn belongs to w, means what? Plus w is equal to w, because x belongs to w means x plus w is equal to w. So this implies c2 times, by definition of a sum of elements in a cosets or the quotient space, we can write this as c2 into v2 plus w plus c3 into v3 plus w, and so on, cn into vn plus w is equal to w. This implies c2 into v2 plus w is what? v2 bar, plus c3 into v3 plus w can be written as v3 bar, and so on, cn into vn bar. This is equal to w. 0, w means 0 element of v by w. Answer now, c2 v2 bar, c3 v3 bar, etc. cn vn bar is equal to w, 0 element of v bar. Okay, but v1, v2, etc. vn are linearly independent. v2 bar, v3 bar, etc. vn are linearly independent by assumption, because according to our hypothesis of the theorem, there exists a basis v2 bar, v3 bar, etc. vn bar as in which the matrix of t bar is triangular. Okay, so accordingly these are linearly independent, means, so what will happen? c2, c3, etc. cn are all zeros. Therefore from relation 1 what will happen? c1 v1 is equal to 0, but v1 cannot be 0 because v1 is a non-zero vector. Therefore the possibility is c1 is 0, means c2 is 0, c3 is 0, etc. cn is 0. Now c1 is also 0. Therefore, by 1 we can declare that v1, v2, etc. vn are linearly independent, and as dimension of v is n, therefore these set of n vectors forms a basis of v. Now we show that the matrix of T relative to this basis v1, v2, etc. vn is triangular. Okay, so I call the set of equations this by A. Okay, this system of equations. Now let's come to the system of equations A. From the system of equations A, we get what will happen? T bar of v2 bar is equal to a22 v2 bar means what? T bar of v2 bar minus a22 v2 bar is 0. This implies T bar of v2 bar means what? v2 plus w minus a22 into v2 plus w is equal to 0. Since T bar of v2 plus w means by definition T of v2 plus w minus a22 into v2 minus a22 into w is w itself. Okay, so this is equal to 0. This implies T of v2 minus a22 v2 plus w. I keep this as it is. Transform this w to right hand side plus w is equal to w. So this is again like x plus w is equal to w means what? X belongs to w means T of v2 minus a22 v2 belongs to w. This belongs to w means T of v2 minus a22 v2 is a multiple of v1 because w is generated by v1 or spanned by v1. So this accordingly what will happen? So T of v2 minus a22 v2 is a multiple of v1. Say that multiple taken as a21. So a21 v1. Therefore what will happen? T of v2 minus a22 v1. a22 v2 is equal to a21 v1 or T of v2 is equal to a21 v1 plus a22 v2. Similarly, for T bar of vi bar is equal to ai2 v2 bar, ai3 v3 bar, etc. aii vi bar, T of vi can be written as ai1 v1, ai2 v2, etc. aii vi. Thus, including the first term is which is when dimension of v is equal to 1. So T of v1 is equal to lambda 1 v1, we have obtained the system of equations as T of v1 is equal to lambda 1 v1, T of v2 is a21 v1 plus a22 v2, etc. T of vn is what? an1 v1 plus an2 v2, etc. ann vn. So if we write the above system of equations in a matrix form, the matrix is lambda 1 into all other terms are zeros. Next term is a21 v1 plus a22 v2 means a21, a22, etc. They are all 0. The n term is an1, an2, etc. an, which is found to be the triangular. Okay. So this is the criterion for the existence of triangular form. This is one of the canonical forms. So the criterion is all the eigenvalues of T must lie in the field. Okay, must lie in the field. So the transformation T to have a triangular form is that all the eigenvalues, okay, all the eigenvalues of T lies in the field. Okay, this is the first triangular form. Let us discuss the other forms in the next class. Thank you for listening.